So in the continuation of working with logic, let's look at the converse of another statement. If x plus 4 equals 4, then x equals 0. Explain whether or not the converse is true. So here my P is x plus 4 equals 4. That's my statement. And my Q is x equals 0. So to write the converse of the statement, Q implies P, we would say if Q, then P. So if x equals 0, then x plus 4 equals 4. So if I guarantee you that x equals 0, is it the case that 4 added to that will still produce 4? Well, yes, because if I take 0 plus 4, that does give me 4. And because that was my guaranteed condition, that whenever x equals 0, x equals 0, then 0 plus 4 will indeed equal 4. And that is a true statement. So here the converse is true, but the converse is not always true. And that's the point that we learned from example 5 to example 6. Now the contrapositive of a statement is a different type of statement. The contrapositive of a statement P implies Q is the statement not Q implies not P. So for instance, if we write the contrapositive of if I am in Paris, then I am in France, we have to write this is P, I am in Paris, once again, that's the P statement. I am in France is Q. And to write the contrapositive, which would be if not Q, then not P. So if I write if I am not in France, that would be the negation of Q. I am in France is Q, so not Q would be if I am not in France. Then not P. Well, P is I am in Paris, so not P would be I am not in Paris. Well, and that's a true statement. In fact, the contrapositive of an if-then statement will always be true, as we'll soon learn. But let's think about this. So here's my drawing of France, and then inside of there is Paris. So if I'm not inside of this circle, then there's no way I'm inside of this tiny little circle that represents Paris, and therefore the contrapositive is a true statement. So how do we prove that these two things, that if P then Q and its contrapositive, are equivalent statements? So let's look at both of those together in a truth table, and notice that all we have here is our P or Q column. P implies Q, not P, and then not Q implies not P. So this is a great way to organize a bunch of statements in here and be able to compare them. So I really want to be focusing on this column and this column to see how are their truth values related. So we know that P implies Q is only false whenever the condition does happen, but the conclusion doesn't follow. Otherwise, that if-then statement is always true. Now, to negate things in a truth table, I'm going to kind of draw a line down the center here just to say that we're still using the same values in the row that we're in, but we're analyzing a different statement. So if Q is true, then not Q would be false. Right? So again, if Q is true, then the negation of Q is false, because a statement can only be true or false. Not P, so if P is true, then the negation of P is false. And okay, well, if I look at an implication, if this, then this, well, just like here, if both of the conclusion and the premise are false, the if-then statement is still a valid if-then statement. Similarly, not Q, when Q is false, that means not Q is true. And when P is true, then not P is false. And hey, wait a minute, that looks exactly like the situation in which the if-then statement is considered false. So here the condition happens, but the conclusion doesn't follow, and therefore that's an invalid if-then statement. Not Q here, so if Q is true, then not Q must be false. If P is false, then not P must be true. So the condition didn't happen, the conclusion did happen. That's a valid if-then statement. Again, remember, the only time an if-then statement is going to be false is when the condition happens, but the conclusion does not follow. And here I'll have, by similar logic, I'll have true, and that, of course, is true. So look at all these truth values. For P and Q both being true, these two statements are both, the output is true. When P is true and Q is false, they both return a false. When P is false and Q is true, they both return a true, and you can see that these columns are identical. Therefore, we could say the statement P implies Q is logically equivalent, meaning they're exactly the same statement as not Q implies not P. The proof of this statement rests in the truth table we showed above. Two statements are logically equivalent if they produce the same set of truth values. And that's a beautiful thing that we can do. We can show that any two statements are either equivalent or not equivalent by showing whether or not they generate the same truth values. Now you can also have statements that are called biconditional, which means that both the original statement and its converse are true. So if the statement holds in both ways, if you switch the premise and the conclusion, which is not always the case. We saw an example of where if I am in Paris, then I am in France, and its converse, if I am in France, then I am in Paris, that converse is not a truth statement. But if they are both true, if you can switch the premise and the conclusion and the if-then statement is still valid, we say that those statements are biconditional. Bi meaning their implication goes both ways, and sometimes you'll see this arrow, and sometimes where people will say P is sufficient and necessary for Q. Basically, P is sufficient for Q to happen, but P is necessary for Q to happen, and you often see people say if and only if. So if you've seen that before in mathematics, I'm sure you have at some point in your math career, then this is where that all comes from. So make an argument for why the statement, if x squared equals 4, then x equals plus or minus 2 is biconditional. Well, first of all, let's start with calling this P and calling this Q. So if I look at the condition, so suppose the condition holds, x squared equals 4. So whenever we go on to prove things in a soon-to-come lesson, we always want to start with the condition and show whether or not the conclusion will follow. So we get to assume that the premise, the condition happens, and now if I go about working with this, so suppose that that's a true statement, well, by using my algebra, if I take the square root of both sides and put a plus or minus on that, this is by just algebraic logic, then that means, well, the square root of something squared is x, and the square root of 4 is plus or minus 2. So you can see that whenever we assume x squared equals 4, the conclusion comes out to be x is plus or minus 2. And that means that we assumed P and we concluded Q. So this was P, and then we concluded Q. If we write the converse of this statement, if Q, then P, the statement that we would generate is if x equals plus or minus 2, then x squared equals 4. Well, let's prove it. So suppose x equals 2. Or x equals negative 2. Well, in either case, if I square either of those two values, in either case, 2 squared is 4, and negative 2 squared is 4, And that allows us to conclude, therefore, x squared equals 4. So we started off assuming q, this was q, that x is either 2 or negative 2. In either case, we established that q squared is 4. We concluded p, so the statement if q then p is a valid one. So what we could say in conclusion is, and these triple dots mean therefore, we could say x squared equals 4 if and only if I'm sorry, I don't need the extra f. Some people will just write IFF to say if and only if, but we're actually just going to go ahead and write it out here. So if and only if x equals plus or minus 2. And that's the general conclusion we can make here. Again, not all statements are biconditional mathematics, or in general, like the if Paris, then France, if I'm in France, then I'm in Paris statement. All right, let's do one more example and then we'll stop it. Let's take a look at a truth table for a compound proposition. So now we have P and Q are some simple statements, and we want to build the truth table for when is this premise and conclusion true. So we have that if P or not Q, then P and Q. And we could look at under what conditions this will evaluate to be true. So what I'm going to do to build my truth table is I'm going to put P and Q in here. And then I'm also going to need not Q in here. So not Q. So I just kind of set up all of the simple statements that I need. Because I do have a negation in here, I am going to have one column for the not Q. It's just going to make it visually easier. And then this statement, 1, which is going to be P or not Q. Remember, an or statement will be true if P is true, not Q is true, or when they're both true. And then I will evaluate the truth values of P and Q. And then finally, I'll look at whether the implication is true or not. Now, this looks complicated, but in order to evaluate this last column, all I need to look at is these two columns here and look at situations where the premise, this being the condition. Some people will call it the premise as well, and the conclusion. So all I have to look at is the condition true? Is the conclusion true? If the condition is true but the conclusion is false, then it's not a true implication. So we can list out all our truth values. We have false, false. We could just do false, true here, and then false, false, true, true. So if Q is false, true, then not Q will be true, false, false. And to establish P or not Q, I only require that one of these two columns, this one, I require just one of those values to be true. And I see that here I have a false or true. Here I have a false, false. Here I have a true, true. And here I have a true, false. All right, good. So now I have the truth values for the condition. Now I want to take a look at the truth values for my conclusion, which is going to be, sorry about that, P and Q. So now I'm looking at these two columns here and here. And the only time this is going to be true is when both of these are true. So we have a false, 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 true, true, false, true, true. And we know an implication, so now we're done with our helper columns. I'll call these helper columns, these first three. And now when we look at the conclusion, remember it's if this, then this. Well, the only time an if-then statement is false is when the premise happens, but the conclusion is false. Premise happens, conclusion is false. So these will be the only two false values we can report. When condition is false, doesn't matter what the conclusion is, the if-then statement is valid. Condition happens, the conclusion follows, that is a valid if-then statement. And so these are the truth values of P or not Q implies P and Q. So when P and Q are both false, this if-then statement is false. When P is false but Q is true, the if-then statement is true. When P is true but Q is false, the if-then statement is false. And when both P and Q are true, the if-then statement is true. And that really wraps up using truth tables. We could really work with more dynamic statements, but what I recommend doing is setting up a column for all of your simple statements and then evaluating it kind of column by column. You can build as many columns or as few as you want, but if you even try to avoid writing down the not Q column and you just try to like intuitively think about, well, if Q is false, then not Q is true. If you're anything like me, you're going to make mistakes by not being explicit in writing this column out. So I highly recommend that you write down all of the columns for all of the simple statements you're going to use and then slowly build up to your final expression.